got here? Okay. I'll get us going here. I'm getting us started a little bit early, so those of you come in later or watch from afar, you'll be able to come in and scroll back and see where we were. And we're going to go down to the modules section. Here we go. And I posted a key. Hi. And if we can, yeah. And once you get logged in, you can join the meeting. But you can always scroll back and see you haven't missed all that terrible much. But we've got from last week, the main thing I uploaded the leisure case. Everybody did pretty well on it. A few people, several people in fact, did all three legs at the same time, which was fine. I could tell that was what had happened, so that was all right. So on the whole, everybody did the leisure pretty well, and we spoke last week about why I had those different scenarios or configurations in there for each of those legs. So no big deal there. It was working with that revenue maximization problem. We're going to encounter a whole new set of problems and applications of this optimizer tool. And I wanted to go ahead and talk about it for a few minutes. We've got three cases that are going to be due this week: County, Foster, and Gorman. And I had also some of the destinations there that you could take and paste those destinations into Easy Map Maker so you could get a sense of where Leisure Airlines, they run an East Coast or kind of a milk run, so you could get a picture of that. Then I also had a link over here to the Boeing 737 airliner, the 400, not the MAX, the small version, and then some information about how airlines handle fares. They make those decisions, and they do use revenue maximization techniques doing them. And then some information about network structure and logistics, composite modeling, because we were dealing with a networking problem, okay, this week, one of them. And then some research studies on DEA. We're going to be looking at data and envelopment analysis, and we'll spend a lot of time on that. And then the HLA, which is Humanitarian Logistics Association. This is anybody that works in logistics that tries to help out with humanitarian crises. So some nice sets of supplemental resources. So if you should ever say this, well, I'm not getting anything that beyond the text. Oh, yes, you are. Here's some good stuff for you to take a look at. Before we take a look at the county case, I want to look at the Foster case. So this is going to be over in pages 259 to 265. And I'm going to search the book for that, and it'll be Foster. And this is a case that involves a supply chain. And that's one of the reasons that this week I included some information about networks and network structures so you can get a sense of how that all plays itself out. Now, as I've said several times, if you were operations management students, if we had a program that here, you'd be looking at network analysis and how networks are put together and all of that. So we'll see a quick and dirty example of that here with the Foster, and it's under a transportation problem. I want to just take a few minutes and let's talk about the setup. And before I do that, I'll just show you what I'm after. Okay, because each week I'll ask you to use that's going to be over in this chapter 6 files. It's Foster. And I ask you just to manipulate, okay, some data, just so you see the model and you understand. And in this case, what I'm asking you to do is increase these supply values for each of these destinations. It will make sense to you as we work through. But I can walk you through through these kinds of problems through the text, so you can get the advantage of some of the good narrative they provide, and you could see some of the schematics that they provide, like the graphics, the tables and figures. It helps make it a less ethereal. But really starting out with this simple problem here in transportation, and you have these 3 plants, okay, that this company has, and they have a 3-month production capacity. These are the number of units that they can manufacture, okay? Now, they distribute, as the case tells us, they generate, I think it's distributed generators, okay, through some regional centers. And now we see the problems start to become another piece of the transportation problem, and that is we have destinations. So over here we have origin points, and then we have the destination points, okay? And then again, you see the 3-month demand forecast, and obviously what we're trying to do is in the supply chain or the transportation problem. Let me stop for a minute also. This is probably about the best definition of a supply chain I've ever seen. And it really does tell you and put everything into context. Now, I would also say this. If you're a management major, which I think most of you are, I'm not sure if we have any other majors. If you're when you get ready to graduate, if you're having trouble finding a place to work, or you're saying, where could I, what's an industry that would be a good place to hang my hat? I'd say right now, the place I would go if I was a student coming out of here with a management degree would be, I'd go try to get a job with any logistics or transportation company I could. The bigger, the better. There are so many opportunities there, and the opportunities for students to go to work, maybe start at an entry-level position and then advance because you have an education, is a tremendous opportunity. And I'm not saying go out and try to become a UPS driver at all. I'm talking about working in their systems offices, their management oversight offices. I have a student who went out to Eaton when we did a visit out there when I used to teach a production course, and he was the only student out of like 30 who sat down and talked to the HR officer, and he ended up getting a job out there, getting some experience. They paid for his MBA. He's working for Butler Manufacturing now, which is one of the largest distributors of components and parts in the country. And I'm certain he's knocking down 6 figures. The folks in the logistics and transportation field are desperate for people, especially management people, who aren't afraid of doing a little bit of work with numbers and who have a good sense or an understanding of supply chain. So I'd say if you're a management major and you leave here and you go, boy, I don't know what my prospects are, that's a great place to go and a great industry. In fact, I had this young man who graduated this spring. He left here. Found a job down in Dallas, and is probably going to have a good opportunity to go for a fast track because people are desperate to get folks. And you need to understand there's 2 things that drive this. One of them is the global economy. If you walk through Walmart, you got stuff made from all over the world, and not even including the extraction piece of that, the materials to get the stuff. So those systems are so sophisticated that it's not the old days where you had people kind of had some experience and grew up in the industry. Thereafter, people who have some background, some decent quantitative skills, but have enough education that they've got a good foundation to come in and work with the applications and the software that they've got. So I would really, really say, encourage you to to take a look at that. The destination nodes here, we have those, and again, balancing out the demand that was forecasted versus what they produced. Now this puts it to you in a schematic fashion, and that's what I want you to take a look at. And this is a network in the simplest terms, okay? And you can see you've got each of these plants which are origin nodes. So when we talk about a network, the circle is a node. It's a place something or some things or money or information or people or all of them together arrive, okay? And then you have a thing called the arc, which is that arrow. And the arrow will typically show you the direction of the flow. So you see you've got these three plants, okay? Then you have the arcs, and each plant, Cleveland, Bedford, and York, each of them feed these four plants. These four distribution centers, excuse me. And here in the middle, the authors have provided for you the transportation cost per unit. You see that? Now, this is a very simple network problem. Depending upon the length of the supply chain, this can get really complex, but there's a lot of, if you go to work, nobody's going to sit you down with and say, graph out our network. You probably work on a piece of software and be trained on it that's designed to help deal with these networks. And the bigger the company, the more complex it gets, or the more complex the product it gets in terms of everything running from the extraction of material, natural materials or resources that are used, all the way up to the finished product delivered to some outlet, or if it's sold online, or both. So you can see these folks are Cleveland, that plant, and the cost the Cleveland plant, the distribution centers that it feeds, and you can see the cost. Okay, as you scroll on down, on the one side, you're going to see the demand, and on the left-hand side is the supply. And as you guess, you're starting to see the right-hand and left-hand sides of the equation. The reason optimization is such a fantastic tool is that it fits so many problems and helps us work through them in terms of either maximizing, minimizing, or trying to hit a target value. So the authors do a nice job of walking us through this. And again, now this is just a simple issue, simple transportation problem. But let's take a look now here at the matrix, and they show you the origin and the destination. Now, the Leisure Airlines case was a little bit of a start to that, because you remember they had those three different legs, and I had you change the demand and the costs on those. It's not any different with a supply chain. In fact, the airline really is a supply chain for all intents and purposes, just pumps people through a system. But basically, you can see here the cost per unit for Cleveland, Bedford, and York. And the whole idea here is we want to minimize the costs. Everybody with me? Okay. Now, the bottom line is this. We're going to use the optimizer to get that accomplished. And as the authors walk us through the narrative, okay, they start to see, we start to build in some of the constraints and the cost expressions, okay, till we can come up with an objective function. And so here's the objective function, and these are all weighted according to the costs. That's the objective function. And then below, you'll see the ST, the subject to, and the constraints that are built in for each of these in terms of demand, or pardon me, in terms of costs based on demand. And the authors do a nice job of walking you through the linear algebra of all that. But the bottom line is this: you're going to have, if you're out there, you're probably going to have something that's been programmed to work with, especially if you're dealing with a transportation or logistics company. There are all kinds of commercial products out there. They require a little bit of training, but after you've gone through training for most of them, you're going to see and understand, be able to use it. Now, here's some of the problem variations, okay? And you can see those at the very bottom. You may have some things like route capacities or route minimums, unacceptable routes. You have to try to weed through all of that. And that becomes building into literally in the applications that people use. They will literally build in, this highway is under construction, or this exit is closed off, it's under construction, or this is a new section, or any one of those variables get built into a more sophisticated product. So we're looking at a pretty simplistic kind of picture here, but nonetheless, these are kind of the variations on it that you have to take into account. When you see these people in the middle of these disasters, especially these hurricanes, the hurricanes that hit these islands, a major issue for them is a critical problem is what we call a bottleneck problem. And that is, most of them are designed to have ports of call to accommodate deep water vessels that come, cruise ships, etc. And so you have a bottleneck. Now, when everything's functioning fine and people are moving in and out, and they move those big ships in and out just like they're in an airport, then if a disaster hits and the whole place is wrecked, and you've got stuff out in the middle of the channel, and you've got all of the equipment that they use all destroyed, and if, even especially if it's still underwater, you got to do something else. It could take you a month or 3 months to even open up a port and get it going. So what they'll often have to do is try to have some alternative ways to get stuff there. And when I talk about stuff, I'm talking about big railroad ship full of railroad cars of material that sits. Well, if you don't have the capacity to do the intake with it, then you have to improvise, and that is an enormous amount of work. If you've not done so, and you ever get a chance to see, the New York Harbor is pretty interesting, but probably the harbor that's the one that will really give you a sense of this is there in Los Angeles. That's probably I think it's our busiest harbor. Probably New Orleans is. But you could see with those tremendous cargo ships come in, the size of those things are immense. And you have cranes that are lifting out these railroad cars and setting them down and sorting them. To try to handle that in a situation where everything's been all torn up is just an enormous amount of work. So they show us here the optimal solution for this problem, okay? And the objective function. And then for each of these variables, those are the routes, okay? And those transportation routes and the value, and where we can reduce some of the costs. And then they show us the optimal solution, okay? And the cost per unit, and what we're going to send from Cleveland to Boston, Chicago, Bedford to Chicago, Bedford to St. Louis, Bedford to Lexington, and then York to Boston. Now, if I were to ask you which of these routes is the most important, what would be your guess or set of routes? Cleveland to Boston could be one because of the total cost involved. Yeah, you're talking about shipping a lot of units. On a bigger scale, in terms of sets of in terms of sets of nodes and origins and nodes, which one catches your eye? Where do we have the highest number of outgoing nodes? Yeah, we got Bedford to Chicago, Bedford to St. Louis, and Bedford to Lexington. So Bedford is a key node for us because it supplies 3 different distribution centers. See it? Okay, so the one that's the largest is Cleveland to Boston. That's an important one. And then you have this set right here. Bedford. So if you're going to have a bottleneck occur, it's most likely it's going to occur with the Bedford. Bedford has 3 outgoing nodes. It's servicing 3 different cities. So something happens there, those distribution centers have an issue. So you might have a situation at a certain point where you would have to maybe offload some of that from York now and send some things out. rather than use it, you'd probably have to end up trying to send some stuff from Bedford to York, Bedford to Cleveland. Then your costs are going to go up. But trying to figure out the most efficient way to do this, the minimum cost, we're going to use the minimization tool. And we'll look at it here in just a minute. But I wanted you to go through the logic of it and see it as we work through the problem. Okay? And then they show us the optimal solution. And it's cleaned up a little bit. Now this is the optimal solution in terms of on paper. Remember that the authors said there's some, they kind of said there's some caveats or qualifiers that we have to be aware of when we try to put these models together, and they can change. They can change very, very quickly. You could see how they've tried to get the supplies and the demands all balanced out. And so that would be the optimal solution. Now, in the Foster, and let's go over here and let's go to the files. And we'll go over and we'll find the Anderson text student, the Anderson text students Excel files, and let's download Foster and look at it in Excel and see what it looks like. So let's grab that. And we'll throw it down there. Obviously, I've got 9 million of them. And we'll open this up and we'll go into chapter 6 and take a look. Now, this is a little bit different problem. There's Foster. I'll throw it out here. Now let's open it up, take a gander at it. And here we are, the generators problem, and here's that matrix that we had, and the supply, okay, and the destination and the cost per unit, okay? And then we're trying to minimize that total cost. And when I click on cell A13 there, I get this sum product. I'm using a sum product of B5D7 and then B17D19. So we're building in those destination costs as well as those constraints into the model. Now it really is that simple. Now, again, getting the figures you put in here is a whole different critter. My wife worked for FedEx for about 15 years, and she worked in the marketing department for them. And one of the things that they had to do is every time somebody would say, well, you know, would say, I'd like to have a FedEx pickup spot here. At one point they would, I think UPS may still do it, but they would have a pickup spot for retailers like in a strip mall. So if they wanted to get some additional foot traffic, they'd kind of deal with UPS or FedEx. People, they'd have little signs that you can drop your package here, and you had to have everything prepared and you dumped it there. So when they get one of these requests, they had to go in and research the whole thing, see how far it was off from one of their existing routes, etc., or the UPS stores, and try to figure out, is this going to be viable for us or not? Making a milk run for a package once a month probably wouldn't be much good to them, but they had to plug in all types of variables to get that figured out. So we look at that and we see this as some product of those costs versus those constraints, and they're the constraints that we built in. And notice it's a classic minimization problem because for all intents and purposes, we're saying equal to or lesser than, okay? And here we're doing the load balancing that's required. And so we have the origins, we have the destinations, and the costs, and the minimum cost. Now, click on data and click on solver, and we're going to see that. All right. Now, in this case, we're going to work on, this is a minimization problem, and you'll see we're going to minimize this by changing the cells B17 to E19. Okay. In other words, here. You see it so far? We've got these destinations, and I'll call it back up here. Now, we're trying to balance these loads so that we keep our costs down. Okay. When we use one of these problems, as I said before, this is a real simple problem, very, very simple. And that's why I ask you just to plug in some data in and play with the model, change some of those costs and see what happens. That's why I put it in there. But this is just this is a straight shot type of distribution problem where I have these 3 origin nodes. I have these, I think, 4 destination nodes, and boom, I'm sending stuff to them. I'm assuming that there's nothing else that has to happen in between. And I'm assuming that the value of what's being carried in there stays the same. That's not always the case. There's what we call value gaining kinds of systems where maybe I send a component to a center that's an assembler, or what we would call a subassembly or a level 1 that puts that component with something else, and maybe it goes on to level 2 and level 3 and level 4. If you have one of those typically in one place, it's probably an automobile manufacturing plant or some kind of heavy goods manufacturing plant. I used to know it, but the mix of materials for automobile manufacturers that comes in the door, in other words, stuff that's ready to go, they just assemble it. I used to know the mix on that on almost every type automobile company. I just don't know it. I haven't kept up with it like I should have. But the bottom line is we're just running this stuff across, so we don't have any assumptions about the value of what we're carrying. You say, well, why did you get into this? Well, I did because we're worried about the cost, right? So if I'm worried about the cost, and let me ask you guys this, the type of cost we're talking about here, is this a fixed or a variable cost? What would you guess? Okay, why? Okay, you change in terms of the volume. It could change in terms of the cost to get the product ready. Yeah, or carrying it. Fuel costs go up, the costs go up, or just the volume goes up. Yeah, it's a variable cost. And so these minimization types of situations are such that we're assuming that the price of this, whatever we're going to sell or distribute, remains the same. The cost becomes an issue for us because we got to suppress the cost as much as we can, because that's what we've got to pay for what? The revenue per unit less the variable cost gives me the fixed cost, right? i.e. the contribution margin. And I need to control that variable cost. So if I have to improve any one of these origin plants, I can do that. Or if I have to improve the destination nodes, I've got that covered. And or if I'm supplying my own transportation. So one of the reasons UPS and FedEx got so big so fast is simple. They cherry picked the toughest. They cherry-picked the easiest routes that the post office had. The post office, the United States Post Office, still delivers more packages than anybody. Most people don't know that. What FedEx said is we'll cherry-pick the stuff and then pay people a premium to get it to them more conveniently and faster. You don't have to go to the post office. You go to a UPS store. Now it's delivered to your door, or both. So they just cherry-picked that because they looked at that problem. Well, nonetheless, I'm going to ask you to change those variables, and I've got that over there in the problem, but you could see, and the one other thing you want to take a look at, we're still working with a simplex LP problem. We're assuming that the costs go up or go down on a corresponding basis. Now, in this case, you would assume the further the distance, the higher the cost per unit. That's almost normally, that's true. There are very few examples where the cost of it goes down on a per unit basis the further you go. I'd like to find one of those because I'd start selling them myself. So, you know, if we ship something to Oklahoma City, to Dallas, it's one thing. Oklahoma City to Phoenix, it's another. Oklahoma City, New York, it's another. So we're dealing with that type of simplex LP where costs will tend to go up. You say, oh, okay, you're talking crazy. Explain. All right, I will. Here are. And this would be the cost, and this would be distance. And as we increase distance, the cost goes up. Now, time is a different issue. On time, well, it's almost the same. If you want a package today, this is time, and you've got the cost. Well, here, I'll make this a dollar sign. If I want it, the faster, the quicker I want it, well, it's inverted. The quicker I want it, the more I pay. Okay. Now, that's Foster. Pretty simple, but a nice way to introduce you to network analysis and network problems. So that's one you'll be working on. Now, we'll go back over here for a sec. And we're also going to take a look at a second case. And that one's the Gorman. Okay. And this one, we're concerned about the total distance between nodes, but the issue for us now is not not just balancing nodes, that is origin or destination. It's also arcs, transportation between where we go from one point A to point B. And I'm going to ask you to change give an increase in the distance for one arc, one pathway, and then the second is a 2.8% decrease in a second arc or pathway. Have you guys taken the production course? Project production course, any of you? You're in it right now. Have you covered PERT CPM, like critical path method? Not yet. Okay. Critical path method is a real simple idea. Let's say that I have an origin point, and I have different paths to get to a destination. Okay, or let's say even different tasks. Well, as I start to look at that network, then maybe I have some intervening destinations. The critical path is usually the one that costs the most or it takes the most time. So I try to look and see, are there slack resources there? For example, if I'm building something, can I stop building this part of it if the supplier doesn't get the stuff in time and keep working on another part? Or if or an airline faces this problem, if our flight to so-and-so is delayed or canceled, then how do I get people to where they want to go using another route? So Foster, the Gorman problem walks us through that. And we'll look at this real quickly here. Let's, I'm going to take a look here at the textbook. We'll take a look and talk about it for just a few minutes. I think at this point, if it hadn't gotten your attention, that boy, I can use this in so many different types of problems. But really, as I've said before, this is really about a way of thinking more than anything. And this is a shortest route problem. Okay. So this time, we're not dealing with the cost of transportation as explicitly. we're dealing with distance. Now, implied in distance is cost, obviously, because we got through talking about that. Typically, the longer the distance, the higher the cost. Make sense? So we're probably going to deal with a linear LP. Same problem, kind of issue here that we're looking at. And we go across here, and we'll come on down, take a look. And the authors do a good job of giving some background. And here's another network problem, but a little bit different. It's not as straightforward as the Foster was, because here we have intervening nodes. This is closer to what you have in the real world, okay? Every time you fly somewhere, you should just be thinking, this is like a miracle. And it really truly is how they balance that many planes in the air at that amount of time, landing flights, coming in and out, getting people to destinations, checking baggage, etc. It's absolutely amazing to me to think about how you can go from one part of the world and go to another part of the world with a relative amount of trouble. My wife and I flew to Europe this summer. I think, let's see, we flew, what was it? 8 hours from Chicago. We flew into Amsterdam. It was 8 hours. And you know, we were riding along at 40,000 feet. You know, you get some turmoil, you get a little bit of turbulence, and you could tell people are nervous flying over the ocean. And that's why most of the time they fly you at night. They don't want you to look at the ocean, and because a lot of people panic. And they go, my God, I'm in a plane, I'm in the ocean. So they'll fly you at night, so you kind of see it, and they make sure as you're coming into land, it's gonna be morning or usually gonna be morning. So we were flying, I was thinking, you know, it's taking us 8 hours, and people are sitting there watching movies. I watched about 6 different movies at one time. It was because everybody had their little movie thing up. And what was really amazing to me is I thought, you know, we did this in 8 hours, and that's a little cramped, uncomfortable, but I wasn't in the bottom of the Mayflower, tossed around in the Atlantic Ocean with animals and sick people and everything else you can imagine. How fast we've come since even just a few hundred years. It's an amazing thing. And there are, if you try, I'm sure if you guys, some of you guys probably fly to go home and you do flight trackers and things like that. It's amazing to me as you watch that. But anyway, they're showing you a more realistic picture here, and they show you their office and then the road distances in miles over to that 0.6. And they give you some information about the roads are all two-way. The flow could be in either direction. So they give you some qualifiers there in terms of what that's going to look like. This is a little bit more realistic. Now, and so as we tried it, and we talked, I mentioned the critical path method for a minute ago. We try to figure out what's the longest, which pathway along here is the longest. Let's look at this first. I started node 1, and I go to 3, that's 20. I go to 5, now I'm at 26. And I go 2 more, and I'm at, so that's 28. Now, if I go node 1 to 2, that's 25. I go to 2 to 4, that's 5. Now it's at 30. And then 4 to 4, that's, let's see, that's 25, 34. If I follow this route, instead of target, I'll just draw it for you. Follow? So I've got 25, 30, 34. This is going to be 26. That's a 7. That's 33. You can see they're pretty close in terms of the critical route, the longest route. And then I've got some slack here, it would appear, but it's not really. This is 25. That's 39. So if I was after the critical path, I'd say it's node 1 to 2 to 6. Follow me? Because that's the highest value. That's the one that's the most likely, the one that I may have to shift some resources from it over into this other routes. Now, again, the authors walk us through this problem, the distances, and then start to construct they begin to construct for us the objective function and the constraints. And these are all weighted given the distances. And you see like the X12, that's node 1 to node 2. The X13 is node 1 to node 3. That's the notation that's going on there. Now, I've made my pitch about logistics and transportation as a career opportunity. And boy, I can tell you, getting stuff to people on time and in the condition they like is a challenging business. And that's why they're always looking for really good folks who are not scared of numbers and really not scared of hard work, and who are willing to kind of step back and see these things as they flow. And again, there's great opportunities out there because it doesn't appear to be that exciting, but I guarantee you, if you're shipping stuff and something happens, then the excitement builds, and then you've got to punt and you got to figure out, okay, well, this has occurred. How do we get the material from point A to point B? What are our backups? When we were over Europe, we took a long tour. We were there for 3 weeks, and I wanted to see. We saw just everything there is to see, and so I don't have to say. I never have to say to my wife, "We're a few hundred miles away. Let's just go there." No, we went. But what was it? So we rode coach quite a bit, and it was enjoyable to me because I was able to kind of get a feeling of how they get stuff transported from one place to the next, and it was really fascinating to me. I didn't see that many freight liners. I didn't see that many huge trucks like we use. A lot of smaller vehicles. So I got the sense that there's a lot of shipment that goes either, probably a lot of, they probably, I think that, well, I do know this, they use their rivers far more than we do. And it was large, a lot of larger vans and vehicles of that size. And just, it seemed like there were all kinds of transportation companies. So I figured they don't have the kind of centralization that we have in this country with having some really, really big dogs. I saw a few UPS. I don't think I saw a FedEx except near around the airports, but I saw some UPS. But a lot more smaller, looked like just small kind of family-owned companies. And that was an interesting thing to see all that. It was, if you've never been there, going on the Autobahn's cool. I wish I'd stopped and we'd stayed so we could drive because we were out. Our coach driver was going about 85 or 90 miles an hour out on the Autobahn. People were blowing by us. One guy came by in a Mercedes. He looked like it was a sports car of some type. I think it was a Mercedes. He looked like he was probably going 150 miles an hour because he was just like, phew. There are no, there are no speed limits there. And that's how the Autobahn, they move folks from one. But it's interesting to see that it looked like they had a less concentrated industry. Well, as you look through here, we could see this in terms of flows. Okay, so these transportation problems or these node problems, when they talk about these flow, this could be transmission of electricity, it could be transmission of water, natural gas, transmission of whatever item or items you've got. And you see the flow out and the flow in. Okay. And we've got that destination node is 6. So it's got 1 unit. So we see the constraint for node 6, and that's how that's written. And then we see the whole thing in its kit caboodle. And it's just, we're minimizing, and we have each of these routes with their notations weighted according to the distance, subject to the constraints for the origin node, and then the transshipment nodes and the destination node. Got it? It's not as complicated as it looks. You see all those X's and all that. That's just the notation for the node of origin. If you look, and we'll pop back over here, and they give us the shortest route problem. Now, another practical application of this is in emergency services. Emergency services people, they have a time window, a window of time that they need to get to people. And I'm sure that they probably would use the same route to my, you know, if I one of these days, if I have a heart attack at home or something like that, which is, or a stroke most likely, you know, they know their route to get there in an amount of time. Now, my wife will be the variable if she decides to wait 20 or 30 minutes before she calls. Who knows? Who cares? I've told her if I'm dropped and my eyes are closed, go shop, have a good time, call them before there's any odor or anything detectable by the neighbors, and come get me. Either. Anyway, as we look here, we see the objective function. We see each of these variables, and those are the nodes. Okay, those are the transshipment nodes, and then the reduced costs and the value that we get from them, and the reduction costs if we use that particular node. And then we see that general linear programming model. That's nice to see. Always remember the two things: the origin node should be 1, the demand should be 1, and then your transshipment nodes are going to be subject to a 0 as you flesh it all out. I wouldn't get too worried about this. What you're going to see in terms of a model or application, or what we've done back here, is going to be more discernible and understandable than just dealing with the general model. I mean, it's fine to know that, but it's all implied anyway. So let's take a look at Gorman. And again, let's go back over into the files section. Well, if you've downloaded the zip file already, which you should have, and I think that's going to be in 6. And here's Gorman. And I ask you to change some of these variables. We're trying to find the shortest route. Notice we have some Boolean language in here. And let's look at it for just a second. If D6, okay, which is that start node, equals 1, then we use that route. Yes. If not, we use it blank. So we're using basically we're using a conditional statement, looking at the start node, the end node, and the distance. And is it the shortest route, yes or no, based upon what we've got to go. Now we see each start node and each end node. So we're assuming we start at 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, or 5, and then we look at the shortest route, unit shipped, and that's how we conform there to that general model. Now let's click on the data for a sec and take a look at Solver. And you'll see what we're doing here. We're minimizing J15, the total distance, and we're changing the cells, that array, D5 to D17. So there they are. Those are our decision variables, okay? And then they have the constraints built in at J7 to J12, okay? And L7 to L12, the right hand and left hand sides in terms of net shipments and then the supply. Again, this is a simplified version of that type of problem, and the authors are giving us an introduction. Network analysis and network analysis would be in itself an entire course. Nothing but that. A whole lot more here than is built in. But the authors, this is an introductory text, so they're letting you kind of get a short little sample or nibble of each of these techniques. So the Gorman, I've asked you to change some of the variables there and do that work. Now, I've got a little bit of time, and I want to do it to introduce us a bit to counties. So I think we're going to have to go back up to, I think county is going to be in 5. So I'll open that back up. And I want to spend a little bit of time talking about data envelopment analysis, because it is probably, of all of the tools that are out there other than network analysis, it's probably used the most. Here it is. Now, the authors do a tremendous job in explaining what data envelopment analysis is all about. And I really don't want to urge you, if there's anything you really pay attention to here in this class, it would be this one, this case. And I'm just going to ask you to upload the file, that's all, because I'm not going to have you changing the variables, because I want us to have some time to talk about it and take a look at it. County introduces us to a concept called DEA, data envelopment analysis. And what data envelopment analysis is about, I'll find those guys here. And they give us some introduction to that technique. DEA is simply a way that we use optimization to create a benchmark by which we can compare a variety of locations or operations, typically locations. In this case, they're going to show us the use of the application of this in terms of hospitals. Now, I'm going to spend some time Wednesday talking about this, because every single one of you is going to encounter this at some point in time. This is a tried and true technique that people use, especially when they operate multiple facilities. This is a hospital here, and if you say, well, is there a real living, breathing example you could point to? And I'd say across the street. That was at one time our little regional hospital that now is owned by a big hospital company. And they use these techniques to evaluate the performance of their hospitals and their clinics. They probably even break it down to use it to look at each of their operations. But I want you to spend some time looking at this case, especially because it's the one that's used the most. And what it does is that we use optimization to create a benchmark by which we compare operations. And so I'm not going to spend any more time. In fact, we start early and I'm going to close this off. But Wednesday, I'm going to spend that entire time looking at DEA and talking about it with you. Okay? All right, folks, thank you. Those of you here and those of you who are out in TV land, I'm going to stop the meeting, and I appreciate it. And if you came in a little bit early, you can catch the front end back on the video.